is ready. Can you see?
Yes, we can see it. Go ahead, Anna.
Okay, thank you. Hello. Let me see. Good morning. My name is Ana Selene Márquez. I would like to thank the organizing committee for the invitation. The title of the presentation is Physicochemical Property, an enzymatic lipophilization of the anthocyanin isolated from Hibiscus sabdariffa. This work was carried out in the University of Chihuahua in Mexico and in the University of Porto in Portugal. Well, we can start knowing that anthocyanins are colored compounds from the flavonoids family and are presented in flowers and in fruits. In nature, anthocyanins are glycosylated in the carbon-2 position of the C ring. And depending on the methoxylation or hydroxylation in the B ring, we can have one of the main 6 anthocyanins, or like pelargonidine, cyanidine, delphinidine, theanidine, pepinidine, or malvidine. Well, one characteristic of anthocyanins is their color display depending on the pH water solution, where we can coexist 5 forms. So at pH below 2, the main species is the phodylene cation with the red color, and at pH 4, the cation suffers a hydration, which can provoke an opening of the ring to form the C-chalcone of yellowish color. And once formed, the cis-chalcone, the isomerization could occur to form the trans-chalcone yellowish too. That means that the anthocyanins are degraded. Well, if the pH in the cation form rises to pH 6, the flavulon cation loses a proton to form a quinoidal base, the bluish color. So these reactions occur at different timing, which is useful to obtain the kinetic constants and to know that the pH, if the pH is 1, 2, what is the mean, the principal species in the solution. Well, other characteristic of anthocyanin is their limited solubility in lipidic media. This poor solubility can has been overcome by lipophilization, which is an attachment of an aliphatic change in order to change polarity. This change has been accomplished by chemical and enzymatic lipophilization. The anthocyanin esters issued from enzymatic reaction keep their color, while the products from the chemical reaction presented a diminishing in their color that affect their potential use as pigments. So we have here the state of the art of the anthocyanin lipophilization. This is a really recent procedure which the most of the reaction has been performed enzymatically. The anthocyanins employed are malvidine, cyanidine, and delphinidine, and most of them were monosaccharides. The enzyme employed was Candida antarctica lipase B, which is selective for primary hydroxyls, although the lipophilization has been reported also in secondary hydroxyls. Well, the raw material for this work was the Hibiscus sabdariffa, which is known as Roselle, Carcabe, or Jamaica, Flor de Jamaica. It's employed for salads, jams, and beverages, and its intake is related to cardiovascular health. The main phenolic compounds in Jamaica is the chlorogenic acid and the anthocyanins, delphinidine sambubioside, and cyanidine sambubioside. Then, the objective of this work is to lipophilize delphinidine 3O sambubioside isolated from hibiscus flower, and we calculate its physicochemical properties. Then, well, the materials and methods are the following. The phenolic extract was performed from dried and grounded hibiscus and then extracted an ultrasonic bath in a ratio of 1 gram of hibiscus powder per 2.5 milliliters of a water ethanol solution. It's acidified water that we use with the work with anthocyanins. So after the extraction, we separated the solvents by evaporation, by filtration, and then we evaporate the supernatant with the low pressure evaporation. Then the anthocyanins were fractionated by solid phase extraction, SPE, employing different solvents by increasing the polarity. Well, after we had the delphinidine pure or isolated, we carry out the reaction, adding the solvent, so 2-methyl-2-butanol, the octanoic acid, the molecular sieves to absorb the moisture from the reaction, the CalB at 60 degrees. While the reaction was monitored by the HPLC MS. And then after the reaction, we stopped the reaction in the maximum yield. After that, we removed CalB and the sieves. We removed also the octanoic acid with an hexane and heptane liquid extraction. And to ensure the absence of fatty acids, we perform thin layer chromatography. After ensuring this absence, we separated the native anthocyanin, or delphinidine sambubioside, from its ester, the delphinidine sambubioside C8. Well, we employed flash chromatography to separate it. After the purification, we performed a mass spectrometry and nuclear magnetic resonance for obtaining the structural characterization, followed by the calculation of the octanol water partition coefficient to obtain the lipophilicity of the new pigment. At the end, we calculate the equilibrium constants by pH jumps and SDC micelles. Well, this consists in spectrum scans of the flavillum solutions for the anthocyanin solutions from pH to from T3 to 8. So then at the maximum absorbance of each of these measurements, we plotted this pH to obtain the equilibrium and pseudo-equilibrium constants here. And well, that's the methodology. The results are the next. Here we have a chromatogram of the whole hibiscus extract. We can see the number 1, the chlorogenic acid, and the number 2, the delphinidine sambubioside, and with the number 3, the cyanidine sambubioside, which were fractionated by SPE, the delphinidine eluted in the fraction 2 and the cyanidine eluted in fraction 3. Next, we can see the chromatograms of those fractions. Fraction 2, we can see only the delphinidine sambubioside with some flavonols, and in fraction 3, we can see the cyanidine sambubioside with some flavonols too. And then after we ensure the delphinidine, delphinidine isolated, we perform the reaction and we monitor the reaction with the HPLC, and the dots are arranged in C8 columns. So here we can see the chromatogram and the The main peak is the anthocyanin, delphinidine sambubioside, and in the time like 14 minutes, we can see the ester. So we do the purifying process and see the ester peak, the fraction of the ester peak, NLHPLC-MS, and we can see the expected mass of 323, which corresponds to delphinidine trisambubioside C8. But also we can see another peak in 591 that corresponds to the delphinidine triglycoside C8, which indicates that we have a hydrolysis in our ester. So we realize we have two products, so we have to change the chromatographic method. So we change for C18 column, and here we can see the chromatogram, and we can observe 4 peaks. The number one is delphinidine sambubioside, and it has an hydrolysis and form the delphinidine glucoside that it's more reactive than the first one. So we have more delphinidine glucoside C8 than delphinidine sambubioside C8. So we change the methodology, because maybe do in a steric hindrance, the delphinidine glucoside could achieve the active site of the enzyme better than the delphinidine sambubioside, so it reacted more. So we change the solvent, and we change also the counter ion of the delphinidine to see if we can obtain a selective reaction without the hydrolysis. So the solvent will still the 2-methyl-2-butanol, but we have to change to formate counter ion for obtaining a selective reaction without hydrolysis. So now here, after obtaining that reaction, we did the purification steps, and here we can see the chromatogram with only the peak of the delphinidine sambubioside C8 ester pure. So with this ester pure, we perform the NMR analysis to see these results. Here we can see a 3 part per million shift from the reported from the pure delphinidine sambubioside. So here we can see we obtained an selective lipophilization on the glucoside moiety of the sambubioside, that was also reported in literature by Cruz and co-workers in 2016. And so next, after confirms the structure of the ester, the first property calculated was lipophilicity with octanol water partition coefficient here. It's shown that the contrastant polarity between delphinidine and its ester. The first one is water soluble, and the ester is soluble in the octanol phase, sorry. So the first one has an index of -3.5, and the ester has an index of 2.2, showing the difference of the lipophilicity. Okay, then the next property was the thermodynamical constants. We obtained the equilibrium and pseudo-equilibrium constants in 5.82 and 5.82 respectively. And with the equations of the constants, thermodynamical equilibrium, we could obtain the hydration constants and the acidic constants, which we can see here. The higher constant of hydration is 6.6, and the low gap between constant of hydration, lower gap between pseudo-equilibrium and equilibrium constant, which means that we have a low concentration or low amount of trans-chalcone in the equilibrium. So with the hydration constant, we can see that the quinoidal base is more stable. So the bluish color is more stable now. So now here we can see with the molar fraction distribution for delphinidine and for delphinidine ester. Here we can see that the flavinium cation for delphinidine sambuvioside at pH at pH 6 we have the normal behavior, and the main species after pH 6 is the trans-chalcone, and then the others. While for
you have
the
1 minute, please, to finish, to wrap up.
Okay, sorry. While the delphinidine ester, we have the main species after pH 6 is the quinoidal base. So we can conclude that the lipophilization of delphinidine sambuvioside extracted from hibiscus modify the polarity of the new pigment, and the lipophilization modify the physicochemical properties of the anthocyanin, making the quinoidal base more a pigment more stable to alkaline pH and less prone to hydration. So the new anthocyanin ester could have a higher potential as colorant in several matrices. Thank you.
Thank you very much, Ana, for your great presentation. Very interesting work related to lipophilization, enzymatic lipophilization. We have time only for one question. If someone would like to ask Ana a question. If it's not the case, then please join me giving Ana a big applause for her presentation. Ana,